Okay, now we're going to look at probability. This is Module 12 of the measure phase in the Black Belt certification course. We're going to look at basic probability concepts and then finish off with a discussion of statistical distributions. So the basic concept is the probability of a given event, E, occurring varies between 0, no probability of it happening, and 1, 100% probability of it happening. So it's always done as a decimal. The sum of probabilities of all possible events, multiple E's, in the then total sample space will always equal 1. So if I had, say, 2 events, sorry about that, 2 events, and there was a probability of 25% of one event occurring, then by process of elimination, the second event has a 75% chance of occurring because it always has to equal to a 1. The ratio of chances favoring an event is to the sum total chances for and against the event. Gives you the probability. So in this case, if the first event has a 25% chance, 0.25% chance of occurring, and the sum total is 1.0, then the ratio would be essentially 1 to 4. There's one chance out of 4 that the event A, which has a 0.25 chance of occurring, will occur. It's always expressed as a ratio, and essentially it's the chances favoring divided by the sum total of chances for and against. A P event is the number of points in the sample space participating in the event divided by the total number of points. So if I want to look at that, okay, there's, I got 100 points, and there's, say, 20 points that actually participated in a given event, say pass or fail. So we'll just call it pass this time around. Then I do the division of that, of 20 by 100 and get 0.2. And the event experiment is repeated. If the experiment is repeated a large number of times, and the event is observed with subscript E times, the probability of E is approximately, and there's the formula for that, PE equals N subscript E divided by N. So there you have that. An event that cannot be decomposed is a simple event. If I cannot sort of break it down any further, there it is. In other words, if I'm flipping a coin, I'm going to either have heads or tails. I cannot decompose heads any further than what it is. I cannot decompose tails any further than what it is. Compound events are formed by composition of 2 or more events. So, for example, if I was looking at rolling dice, and I was looking for what is the chances of my rolling under 3. So in other words, is my dice rolls going to be less than 3, then there are essentially it's a compound event because I'll be combining the odds of rolling a 1 with the odds of rolling a 2, and together they will form my compound event. 2 most important probability theorems related to compound events are the additive and multiplicative theorems. And so we'll look at compound events again. We'll look at the example over here. And the composition consists of 2 possibilities, a union or intersection. A union of A and B is represented as that. And basically, that is, if A and B are 2 events in the sample space, the union of A and B contains all sample points in event A or B or both. So if I was going to look at, say, the example I was giving, basically, if I'm rolling just 1s, basically we have that. If I'm rolling just 2s, we have that. And of course, we could have, if I'm rolling a mixture of 1s and 2s, then of course they also form a union. Intersection of A and B is if A and B are two events in a sample space, the intersection of A and B is composed of all sample points that are both A and B. This is your classic Venn diagram scenario where we have here, and this is here like that. So everything that's in here is in the intersection space. There we go. There it is. Event relationships. There are three relationships in finding the probability of an event. They are complementary, conditional, and mutually exclusive. Complementary is a complement of event A is all sample points in the sample space, but not in A. Therefore, the complement of A is 1 minus PA. So the conditional probability of event A is given that B has occurred is, and there's a formula for that. And we're continuing there. The two events A and B are said to be independent if either this happens, if either P, the union of A and B is A, or union of A and B, BA is B. Otherwise, the events are said to be dependent. Mutually exclusive, if event A contains no sample points in common with event B, then they're mutually exclusive. Means you have all your A's here, you have all your B's here, and neither the twain shall meet. Testing for event relationships. Are events A and B mutually inclusive, complementary, independent, or dependent? Well, if events A and B contain two or more sample points in common, then they are not mutually exclusive. If event B does not contain all the points in the S, then they are not in event A, then they are not complementary. You have the additive law. If two events are not mutually exclusive, that's the formula for that. If two events are mutually exclusive, the additive law reduces to this. Note that the designation that P, A, and that symbol there is also shown as A plus B in some texts, and is read as a probability of A or B. The multiplicative law, if events A and B are dependent, then the probability of A influences the probability of B occurring. So this is known as conditional probability, and the sample space is reduced as follows. Or if events A and B are independent, then it looks like that. Expected value equals the sum of the values of each outcome multiplied by the probability of each outcome relative to all other possibilities. E in this case represents the expected value operator, and V represents the variance operator. And there's the formula for that. And if it's a random variable and C is a constant, then you have this. Okay, permutations are an ordered arrangement of n distinct objects. The number of ways to order the distinct objects is taken r at a time. Is designated by the symbol Pn. Though some texts will also use Pn, comma r or npr. And here's a counting rule for that. Combinations is the number of distinct combinations of n distinct objects taken r at a time. It is denoted by the symbol Cn, though some texts will actually use these symbols instead. And here's the rule for that. Normal distributions, we'll do a continuation of discussion on normal distributions for Module 11. We're looking at what makes a distribution normal. Well, only random error is present. The process is free of assignable cause. The process is free of drifts and shifts. That means as we're doing our process, is our tooling or whatever shifting, so our tolerances are basically what we're outputting, the tolerance is kind of pushing over this way, pushing over this way, pushing over this way. So as we said, the normal curve is smooth, symmetrical, bell shape, and is generated by density function. There it is. It's a very pretty one. This really shows you everything you ever want to know about a bell curve, including your z-score, your standard deviation, cumulative percents. There it is for your percentiles. And each combination of mean and standard deviation will generate a unique normal curve. So you may end up with something fairly flat like that, or something with a very pronounced kurtosis, and so on and so forth. Data from any normal distribution can be made to fit the standard normal by converting raw scores to standard cores. The z-scores measure how many standard deviations from the mean a particular data value lies. The empirical rule, we've talked about that. Basically the percentages, 68.27 lie within one standard deviation of the mean, 95.45 lies within two standard deviations, and then 99.73 of your values lay within three standard deviations. And there's a chart there that shows that. Non-normal data. While normally distributed data needs to be used to calculate a sigma, there are alternatives if you are faced with non-normal data. In some cases, you can transform your non-normal data into a normal distribution via the use of logarithms to a normal distribution. If you're interested in doing so, you can look up the formula for that. Binomial distributions they're useful when the populations exist in only two states, free of, basically it works or it doesn't work, pass, failed, is there a defect or not, yes, no, these sorts of situations. They only apply when the trials are independent and the number of samples of the population is fixed. The distributional parameter is the average proportion. The value is assumed or calculated by dividing the number of sample items that meet the condition by the total number of items in the sample. So it's simpler. In many ways, it's very much related to doing probability in that sense. And the binomial distribution versus normal distribution, it shows how that works. We have the normal curve over here, and you have your binomial distribution over here, and using these two colors. A Poisson distribution guesses the number of times a particular condition will occur for a given process or population, such as non-conforming or defective units. The distinguishing feature is its appropriateness for the situation in which targeted conditions may occur more than once for each unit. In other words, if you could have multiple defects, I'm producing shirts, and I'm looking at sort of like loose threads or loose seams or stains, I can count those. And I would be using this tool for that. It basically used to accurately estimate the number of events for each sample unit. The trial should be independent, and the data should be composed of positive whole numbers. We're looking, which kind of makes sense when you think about it. I'm not going to have -1 defects. I'm either going to have no defects, 1 defect, 2 defects, 3 defects, and so forth. The distributional parameter is the average number of instances per unit. So are we averaging what? 2.6 loose threads per shirt, whatever it is. And that's what the plot looks like. The horizontal axis is the number of occurrences, and the CDF is discontinuous at the integers of k and flat everywhere else, because a variable that is Poisson distributed can only take on integer values. And here are the formulas for it. Student's T is used to express confidence intervals for a set of data and to statistically compare the results of different experiments. The t-test is also valuable to compare two different sets of data to determine if they are the same or different. It's similar to a standard normal distribution. It has a larger spread about 0 due to increased variability due to using a sample rather than a population. Uses critical values under the t-distribution table. You assume that your population is normal, although it can be relaxed if your sample size is large. Random samples were drawn from the population of interest. As the sample size increases, in other words, the degrees of freedom increases, the t-distribution approaches the standard normal curve. If the absolute value of the test statistic is greater than the critical value, then we reject the null hypothesis. So this is greater than that. There we go. And here's what it looks like. As the sample size increases, it gets closer and closer to what the standard normal distribution is. And there we go. Basically, we're looking at the critical values with probability lying to its right. It's fun by looking things up on a t-distribution critical values table. You'll have a table, you generate the number, you look it up, and there it is. And they look like that. And this is for one-tailed. One-tailed is, again, we're looking at just this over here. We're not interested in what's happening over here at all. So we're not interested in this at all, just over here. So that's called one-tailed. If we were interested in both, this would be then two-tailed. If we were actually looking at this too as well as that, then it would be two tails. You can do that, or you can use, if you're using Excel, you can use this function, although you'll have to double the probability because it assumes two-tail results if you're only interested in one tail then. There we go. F distribution, can you use this to either test the equality of variance, test the equality of population means in ANOVA, test for regression models, slopes relating to one continuous variable to another, which is what a regression model is. There is different F distribution for every possible pair of degrees of freedom. There are two sample variances involved and two sets of degrees of freedom. The expected value of any F distribution is 1 if the null hypothesis is true. So if we have no effect there, that whatever I do to y has no effect on x, then the distribution will be 1. And there's the formula for that. And the curve looks like this. Here we have, there's obviously, we have no effect here. And then we just go along this way, we have more effect. And then you have hypergeometric distributions. We're looking at when our sample is a relatively large proportion of the population. In other words, probably more than 10% of it. And the sampling is done without replacement. That means if we draw something out, we don't put it back in and try again. And the formula and curve are below. And continue on with more of the formulas. A bivariate distribution is a joint distribution of two variables. Bivariate distributions may be either discrete or continuous. They may be either a total independence of two independent variables or a covariance between them. The normal density with correlation coefficients formula is below. And if you graph it, it'll look like that. Exponential distribution is used to model items with a constant failure rate that is closely related to a Poisson distribution. If the random variable x is exponentially distributed, then the reciprocal of x follows a Poisson distribution. Likewise, if x is Poisson distributed, then the y equals 1 divided by x is exponentially distributed. And the formula for that is there below. And the graph looks like that, and the variance formula is that way. So there's one thing that characterizes is the hazard function, which is constant, which means that the probability of survival for a time interval is dependent only on the length of the interval, not on the time from start to finish. So if we're looking, for example, at the odds of a defect occurring, it's not going to change during the course of the day. At any given point, say we're sampling every, over a period of 10 minutes, the hazard rate will stay the same. It won't be different, 4 hours into our process than it was, at the start of the process. Log normal distribution is the most common transformation The most common transformation is made by taking the natural logarithm, but any base logarithm such as base 10 or base 2 may be used. The formula looks like that. And the graph looks like this. And the means and variance are below. Weibull distributions is widely used for reliability in statistical applications. The 2 and 3 parameter Weibull are common versions. The difference is the 3 parameter Weibull distribution has a location parameter when there is a non-zero time for the first failure. The 3 parameter probability density function is below. And again, so this is the end of Module 12. We looked at probability basic concepts, and we showed some of the statistical distributions that you will encounter along the way. We'll continue with Module 13.